Hey, what's up? In today's video, we're going to talk about unequal load balance in EIGRP. If you remember one of my previous videos with name Dive into EIGRP, with the EIGRP introduction concept, you remember that, right? I once told you that EIGRP is the only IGP that you can implement unequal load balance, which is really interesting, by the way. So in today's video, we're going to talk about unequal load balancing a little bit, about the conditions that are the prerequisite to use other links and routes to conduct a packet to reach the destination. And then we're going to configure and implement unequal load balance in real scenario, which is really practical, guys. Now, I want to talk about what we have learned before. Guys, we have learned that in normal situation, in a routing protocols, we have only one link with the lowest metric, which is named feasible distance, that all of the packets go through this link to reach the destination, right? And we also learned that if we have several routes and links along the way with the same and equivalent metrics, it's going to be load balance, and all of the links are going to be installed in the routing table. But now my question is, what is exactly unequal load balancing? Guys, unequal load balance allows traffic to be distributed across several routes with the different metrics. Okay, I give you an example. I'm EIGRP. I want to use both of these links. This link is gigabit interface with the bandwidth 1,000,000 kilobit per second. And this link is fast Ethernet with the number of bandwidth 100,000 kilobit per second. We're supposed to use both of them at the same time, so we have to implement unequal load balancing in this scenario, right? Now, I give order. 1,000 packets go through a gig interface, this link, and 100 packets go through fast Ethernet, this link. This is unequal load balance, and as you can clearly see that this is a very smart mechanism, guys. Okay, now let's jump into the laboratory. Before getting into the laboratory, guys, you might ask me, what are the benefits to use unequal load balance? Well, there are several reasons, but the first reason is we actually can decrease the pressure on the feasible distance link, right? And another reason is we can increase the number of bandwidth because we use other links to conduct the packets to reach the destination. Okay, let's jump into the laboratory. As you can see, there are several routers here. Router 1 at the start, and there are 5 links in the middle. Router 2, 3, 4, 5, and 6. And there is another router 7 at the end, which is connected to our LAN with the name network 10. To start the task, I'm going to show you topology table with IP, EIGRP, topology, all links. Here we go, this is network 10, and as you can see, all of the links have the same metrics, and they are equal to our feasible distance, 21, 76, 0, right? As you can see, these are our metrics. Are all the same. And another thing we have to check it out is EIGRP protocol. Here we go. As you can see, we have already configured EIGRP classic mode with AS number 10. And there is something very important in this information is maximum metric variance. Guys, I'm going to explain completely what variance number is in this video. Don't worry about that. But right now we have do with this one, maximum path. If you remember if you watch my previous video in equal load balancing, we have some important concept about number of maximum path. And I told you in that video, in Cisco, whatever the number of your routers you want to have in your topology, the system allows you to install only 4 links in your routing table. 4. So because we have 5 links and want to implement unequal load balance, to first of all, I'm going to increase the number of maximum path. So we get into EIGRP configuration, AS number 10, and we can easily input maximum path. And in this case, I'm going to input 5 because we only have 5 links. All right. Okay, now show EIGRP protocol. Here we go. Our maximum path is 5 now. Okay, to start the task, we have to change the number of bandwidth for each interface. As I already wrote down in here, to start the task, we're going to change the number of bandwidth for interface. So we get into interface. What is that? PO1/0, right? You know better than me how to change bandwidth and delay, right? Bandwidth, what is that? PO1/0 is 1544 kilobit per second. Guys, because this is just a laboratory and I just want to show you unequal load balancing implementation properly to understand the concept better, I'm going to change the number of bandwidth and delay, but you should never ever touch your device's number of bandwidth and delay. You get into trouble, guys. You believe me. But this is just a laboratory and I want to show you unequal load balance. That's why I changed the number of bandwidth and delay. Okay, you never do that. And then now I'm going to speed up the video not to waste your time, and then continue our project after getting done with changing the number of bandwidth. All right, let's go. Okay, now we have done with changing the number of bandwidth in all of the interfaces. Now it is time to change the delay number for all of the routers that are participated in this topology. I have already wrote some script here, so I'm going to copy and paste in all of the routers. Router 1 to change the delay number. Sorry. Okay, copy, paste in router 1. Great. Router 2, router 3, 4. All of the links are going to be 1500 microseconds for delay number, right? Router 5, 6, and the last one 7. And shot and no shot, because this is emulator. I don't want any bug while I'm doing my scenario right now. Okay, all of the delay numbers are changed right now. Now it is time to implement unequal load balancing in our scenario. But before that, I want to tell you there are two conditions to implement unequal load balancing in EIGRP. Number one condition is we have to the feasible distance number must be bigger than RD. What is RD? It is reported distance. To see reported distance, we get into topology table, show IP EIGRP topology. Oops, EIGRP all links. Okay, now here we go, network 10. And as you can see, the feasible distance is now 424, 26, 11, 2. And all of the metric numbers are changed now. As you can see, they are changed. And what is RD, or reported distance? This number is our reported distance, or RD. And the first condition is we have to, the feasible distance number must be bigger than reported distance. So as you can see, our feasible distance is bigger than this one, router 4 here. It is smaller than this link, router, guess what? 45. This link, router 5. So it's gonna be out. This link, router 5, with router 5, this link is gonna be out because it's a very tiny and very too weak interface. And feasible distance is actually bigger than this one as well. This link, router 3, this route. And feasible distance is actually smaller than this link, the router 6, with number of bandwidth 1000. As you can see, the components of metric are too weak. As you can see, the number of bandwidth is very small and the delay number is too weak. So there are only 3 links to participate in unequal load balancing scenario. All right, there are only router 2 through router 2, 3, and 4, and router 5 and 6 are out. And we have to check out condition number 2 to make sure that these 3 routes are going to participate in unequal load balance, and they're going to continue our project. So we're going to, first of all, let me tell you that condition 2, what condition 2 is. It is you have to multiply your feasible distance by your variance number. What is variance number? Guys, variance number is used in EIGRP to implement unequal load balance. So in EIGRP scenario, variance number is 1 by default. So to change the number of variance, we have to get into EIGRP configuration again. The condition is we have to multiply feasible distance by the variance, and the answer must be bigger or equal than CD. What is CD? It is a metric. Where is that? This is CD. This is CD, the metric, right? So we're gonna change the variance number first. Conft router EIGRP AS number 10, and we can easily input variance and the number. We can input 1 to 128 actually, but in this case I input 2. So the variance number is 2 now. And after that, let me open the topology table again, show IP EIGRP topology, all links. Okay, we have to multiply the feasible distance number by variance number, that which is 2 right now, and the answer must be bigger or equal than CD. What is CD? These metrics, the calculated distance. So as you know, because of the condition 1, because of the first condition, router links through router 5 and 6 are out, and there are only 3 links, these routers and links. All right, now let's check it out. Let me open out my calculator to calculate the answer. Copy feasible distance number, and multiply by variance number. What is the variance number? Is 2, right? And the answer is this. So we're gonna check it out with the metrics. So it is bigger than, let me see, router 2, 3, and 4 are left. Router 2, 3, and 4. And the answer is bigger than the first one. So the first one wins the condition. The second one, 2 million. So the second one wins the condition as well. And the last one, the answer is bigger than the last one, which is through router 4. So we have 3 routers in unequal load balancing scenario. And if I show routing table with IP route, we're supposed to see these 3 links in a routing table because they are the winner in conditions, unequal load balancing condition. IP route, we're looking for network 10. Now here we go. As you can see, there are 3 links left that all of the packets are be distributed through this link to reach the destination. As you can see, this is the metric, and this is our feasible distance through router 10.2, the first router with the number of bandwidth 1544 kilobit per second. Now our project is done. Thank you guys for watching. I hope you enjoyed that. I'm planning to finish CCNP course very soon. I really hope so. If you like my video, you can subscribe and like my video to watch more videos like this. You can support me with that. Actually, it means a lot for me. Thank you. See you soon.